Well, hello there, Chemistry 20s. I just had a little Google Meet with a couple of your classmates. Thanks to those of you who were able to join me. So I'm just going to create a short video. I went into a lot more detail in the Google Meet, but just a little bit of feedback from our assignments from the week of April 20th. So with the formative on solutions, most students had trouble, not most students, some students had trouble with being able to comprehend this chart and being able to justify their answer. So here's an example of a question. The lab technician is identifying solution 1 as KCl. Well, that's an ionic compound. And so identify if the lab technician is correct or not. So you go up and you look here. Here is chemical number 1, but wait a minute, it says it's not conductive. Well, how can that be? This is an ionic compound that they have, and ionic compounds make ions in solution, so it would be conductive. So that doesn't fit with our knowledge about ionic compounds. So your answer had to talk about the fact that when you have an ionic compound, it is going to make ions in solution. So it will be an electrolyte, it will conduct. And that's why this student didn't get marks. Okay, so if you said all this, that's how you do get 1 mark, right? So that solution obviously had to be molecular because it's not making ions and it's a non-electrolyte. That's why there's no conductivity. So that's kind of related to this next question, right? Number 5 says all the solutions were electrolytes. Well, were they really? If they're electrolytes, they're all going to conduct, but we just said that solution 1 doesn't. So again, that lab technician is incorrect here. You have to look through and decide for yourself, are they all conductive? Well, this solution was not. So you know that was a molecular compound. And so that's what your reasoning, your justification had to talk about. Solution 1 was not conductive. So it was not an electrolyte. This statement is not correct by what the lab technician said. Okay, here's another statement saying none of the chemicals were classified as basic. Well, you guys know from Science 10 that if it's a base, red turns litmus goes from red to blue. And so clearly chemical 3 is a base. So this is obviously not correct. And there is a base, and it is chemical number 3. And the reason why it is basic, well, bases are basic because they have hydroxide ions. So somewhere in your justification, you should have talked about justification that, you have red litmus turning blue because of hydroxide ions. Okay, we also had our bonding summative, and a lot of students got this question wrong, this numerical response. A lot of students selected 1 as a correct statement. It is not a correct statement. The correct statements are 2, 3, and 4. So it says all valence electrons are used to form bonds. Well, I challenge you that, and I'm going to ask you, so then what's a lone pair? So here's an example of an ammonia molecule. And it has a lone pair of electrons right here. Is that forming a bond? No, it's not. So not all valence electrons are used to form bonds. Lone pairs do not, only bonding electrons. So if you look at a nitrogen atom, it has 1 lone pair, but it has these 3 bonding electrons, and the bonding electrons are what is going to form a bond, not the lone pair. Okay, let's see what we got next. Type of bond between hydrogen and nitrogen inside the ammonia molecule. Well, I think maybe students didn't read carefully here because more students actually answered this incorrectly than what was correct. The correct answer is this is a polar covalent bond. And so how did I know that? Because I'm looking inside or within the ammonia molecule. It is an intramolecular bond. A molecule has covalent bond by sharing electrons. Now, they are not shared equally. The nitrogen has an electronegativity of 3, whereas hydrogen is 0.2. So this value, that electronegativity difference of 0.8, falls within that polar range of our bonding continuum. So that is not a hydrogen bond. A hydrogen bond is found between ammonia molecules or between water molecules. So it is an intermolecular force and attraction that is going to be between 2 different or to similar molecules. So we know that we have this very electronegative, partially negative nitrogen atom, which is got a lot of electrons around it, right, because of its high electronegativity. And so hydrogen, which is, partially positive, of one molecule will be attracted to another molecule of ammonia, the N, which is more negative, right? Because negatives and positives are attracted. So this is between two molecules, not within the molecule. So this guy here is an intramolecular force inside of or within a molecule. This force that attracts two molecules together is intermolecular, and that is a hydrogen bond. So maybe the confusion came about. I said that for there to be a hydrogen bond, molecules have to have FON. So that means they have to have a covalently bonded F to H or O to H or N to H. But this is the covalent bond that's found within the molecule of ammonia or water or whatever. And the intermolecular force, as we see here, is between the two molecules. Okay, so there was some confusion on that question. Maybe sorry if it's stemming from me and how I phrase things. Okay, the next question that a lot of students had trouble with was on ionic and covalent bonding, and you just had to pick the properties that apply to covalent bonds, which we know are in molecular compounds, and they are very strong, and they're between two nonmetals. And if you look at the electronegativity difference, we know that we either have nonpolar covalent bonds, which range from 0 to 0.4 for their electronegativity difference, or we have a polar bond, which is 0.5 going up to 1.7. If you compare that to an ionic compound or a molecule that acts or behaves like an ionic compound in the continuum, it is going to have an electronegativity difference of 1.8 to 3.3. So yeah, covalent molecular compounds are going to have a smaller difference. So the actual correct answer was D, 2, 3, 6. D was correct. Okay, many students selected 1, 3, 6 or 2, 4, 5, right? So they're not reading or not understanding about covalent compounds. Okay, a couple more questions. This is the one that unfortunately I made an error on and I marked wrong. And so I've adjusted your scores. I apologize for the error. That was my mistake. So anytime you guys are asked about polar compounds, you have to do two things. You have to look at the electronegativity difference between the atoms, and you also have to draw the molecule out so you can see the shape. So this is now the correct answer. The most polar molecule is HF. In fact, it's within the ionic spectrum of our continuum, right? It's got such a high electronegativity difference. It's very, very, very polar. And then ranking the electronegativity differences, right? The guy with the least electronegativity difference, well, he's going to be the least polar. He's non-polar. And then 0.4, well, that's a little bit higher, so that's why methane is the second one. And then comparing these electronegativity values, well, the highest value is the most polar, so the next highest value would be the next most polar, okay, the next biggest electronegativity difference. Okay, so I apologize, I have corrected that. Your mark will now reflect it. There was an error in the key. Comparing boiling points, again, you're always looking at intermolecular forces, and so you have to decide what is the dipole-dipole, is there London force, and is there a hydrogen bond? Well, everything has London forces, right? These molecules all have an OH, so each and every one of them is polar. They have a dipole. And due to the nature of the OH bond being attracted to the OH of another chemical, they have a hydrogen bond. So what could be different between them? What is causing this guy to have the lowest boiling point and this guy to have the highest boiling point? Well, it's the size of the molecule. This guy has 1 carbon, this guy has 2, and it goes up to 5. So the size of the molecule, the number of electrons, is making the difference here. So the answer is because of the molecular size. Okay, the polarity is not changing, hydrogen bonding is not changing. In fact, what's happening is the size is increasing, and that's why the boiling point has gone up. Okay, this numerical response, we've got 2 to finish up here. Again, when you are asked about boiling points, when you're asked about intermolecular forces, you must draw out the stereochemical shapes, right? You have to look and decide what are the London forces? What are the dipole? Is it a polar molecule or not? That's why you got to draw it out to look at the shape. And then does it have a hydrogen bond? So a lot of students maybe picked, ooh, well, this guy must have the highest boiling point because he has the most electrons. That's not true, because when you are comparing, you have to look at the strongest of these intermolecular forces. These count more because they're stronger forces than the number of electrons. And so when you look at a molecule like water that is got a very high electronegativity difference, is a polar molecule, and has the strongest intermolecular force, a hydrogen bond, then he is actually going to have the highest boiling point. You see that, yes, he does have the highest boiling point. Okay, and so I accepted 2 different answers here, but a lot of students still struggled with that. You've got to draw these out, guys. Same for this last question, right? Draw out the molecule. Who's got London? Who has dipole-dipole? Are they polar or not? Draw out the molecule. And do they have hydrogen bonds or not? Okay, so very important. These questions take a long amount of time, but they're worth it in the end. Okay, so just an FYI, this week we're doing more on the solutions unit. You're going to see me talking about, does it dissolve? So non-electrolytes will dissolve. They will become aqueous but stay as molecules. Ionic compounds are going to dissociate. They are going to become ions in solution. Why? Because they're made of ions in the first place. Or does it ionize? Is it an acid? Does it make ions? Does it start as a molecule? And then does it become ions in solution? Okay, well, that's it. That's all I got for you. And I guess that's it for now. We'll talk later.